1,4-dioxane, often simply called dioxane because the 1, 2 and 1, 3 isomers of dioxane are rare, is a heterocyclic organic compound. It is a colorless liquid with a faint sweet odor similar to that of diethyl ether. It is classified as an ether. Dioxane is used mainly as a stabilizer for the solvent trichloroethane. It is an occasionally used solvent for a variety of practical applications as well as in the laboratory. Synthesis and structure: dioxane is produced by the acid-catalyzed dehydration of diethylene glycol, which in turn arises from the hydrolysis of ethylene oxide. The molecule is centrosymmetric, meaning that it adopts a chair conformation, typical of relatives of cyclohexane. The molecule is conformationally flexible, and the boat conformation is easily adopted, as required for chelation to metal cations. In 1985, the global production capacity for dioxane was between 11,000 and 14,000 tons. In 1990, the total U.S. production volume of dioxane was between 10,500,000 and 18,300,000 pounds. Dioxane has 3 isomers, in addition to 1,4-dioxane, 1,2-dioxane and 1,3-dioxane are also known. Uses: dioxane is primarily used as a stabilizer for 1,1,1-trichloroethane for storage and transport in aluminium containers. Normally aluminium is protected by a passivating oxide layer, but when these layers are disturbed, highly reactive metallic aluminium is exposed to the chlorocarbon. This aluminium reacts with 1,1,1-trichloroethane to give aluminium trichloride, which in turn catalyzes the dehydrohalogenation of the remaining 1,1,1-trichloroethane to vinylidene chloride and hydrogen chloride. Reflecting its properties as a ligand, dioxane poisons the aluminum trichloride catalyst, by formation of an adduct. Apart from its use as a stabilizer, dioxane is used in a variety of applications as a solvent, for example in inks and adhesives. Solvent properties: diethyl ether is rather insoluble in water, whereas dioxane is miscible and in fact is hygroscopic. At standard pressure, the mixture of water and dioxane in the ratio 17.982.1 by mass is a positive 8 ceotrope that boils at 87.6 A degrees Celsius. Dioxane is a versatile aprotic solvent. The oxygen atom is Lewis basic, so it is able to solvate many inorganic compounds. Because of its lower toxicity, it is substituted for tetrahydrofuran in some processes. However, it has a higher boiling point, which is important when reactions are to be conducted at a higher temperature. The oxygen centers are Lewis basic and so dioxane serves as a chelating diethyl ligand. It reacts with Grignard reagents to precipitate the magnesium dilide. In this way, dioxane is used to drive the SCHLENK equilibrium. Dimethyl magnesium is prepared in this manner: 2CH3MgBr plus 2MgBr2, C2H4O, 2 plus 2 mg. It is used as an internal standard for proton NMR spectroscopy in D2O. Toxicology, safety: dioxane has an LD50 of 5170 mg per kilogram. This compound is irritating to the eyes and respiratory tract. Exposure may cause damage to the central nervous system, liver and kidneys. Accidental worker exposure to 1,4-dioxane has resulted in several deaths. Dioxane is classified by the National Toxicology Program as reasonably anticipated to be a human carcinogen. It is also classified by the IARC as a Group 2B carcinogen, possibly carcinogenic to humans because it is a known carcinogen in other animals. The U.S. Environmental Protection Agency classifies dioxane as a probable human carcinogen, and a known irritant at concentrations significantly higher than those found in commercial products. Under Proposition 65, dioxane is classified in the U.S. state of California to cause cancer. Animal studies in rats suggest that the greatest health risk is associated with inhalation of vapors in the pure form. Like some other ethers, dioxane combines with atmospheric oxygen upon prolonged exposure to air to form potentially explosive peroxides. Distillation of dioxanes concentrates these peroxides, increasing the danger. Environment: dioxane has affected groundwater supplies in several areas. Dioxane at the level of 1 gram per liter has been detected in many locations in the U.S. In the state of New Hampshire alone in 2010 it had been found at 67 sites, ranging in concentration from 2 ppb to over 11,000 ppb. 30 of these sites are solid waste landfills, most of which have been closed for years. It also has low toxicity to aquatic life and can be biodegraded via a number of pathways. The problems are exacerbated since dioxane is highly soluble in water, does not readily bind to soils, and readily leaches to groundwater. It is also resistant to naturally occurring biodegradation processes. Due to these properties, a dioxane plume is often much larger than the associated solvent plume. Cosmetics, as a byproduct of the ethoxylation process, a route to some ingredients found in cleansing and moisturizing products, dioxane can contaminate cosmetics and personal care products such as deodorants, shampoos, toothpastes and mouthwashes. The ethoxylation process makes the cleansing agents, such as sodium lauryl sulfate, less abrasive and offers enhanced foaming characteristics. 1,4-dioxane is found in small amounts in some cosmetics, a yet unregulated substance used in cosmetics in both China and the U.S. In 2008, testing sponsored by the U.S. Organic Consumers Association found dioxane in almost half of tested organic personal care products. Since 1979 the U.S. Food and Drug Administration have conducted tests on cosmetic raw materials and finished products for the levels of 1,4-dioxane. 1,4-dioxane was present in ethoxylated raw ingredients at levels up to 1410 ppm, and at levels up to 279 ppm in off-the-shelf cosmetic products. Levels of 1,4-dioxane exceeding 85 ppm in children's shampoos indicate that close monitoring of raw materials and finished products is warranted. While the FDA encourages manufacturers to remove 1,4-dioxane, it is not required by federal law. See also, 1,2-dioxane, 1,3-dioxane, crown ether, sodium lauryl sulfate, oxalic anhydride, dioxane tetractone, references.